All right, everyone, welcome to our next topic. We're going to be going through the ignition system of an automobile and getting a brief understanding of the technology that's involved in the ignition system and how it works in our daily lives. All right, our main focus after we go through this presentation would be to explain the operating principles of the automotive ignition system. I want you to have a vision in your minds of the primary and secondary circuits of the ignition system. And then I'll go over the components so that you're able to describe the basic functions of these components that make up the ignition system. We're going to compare the different items such as ignition coil, spark plug, and different ignition circuit variations. We'll talk about a coil pack and direct ignition systems, and again, all trying to prepare you for the ASE exams that you'll be taking in the future. So the first thing for us to understand is that the ignition system takes our initial battery voltage from our charging system and amplifies it to over the greater than 40,000 volts. And this is what delivers the voltage or spark that we see at the end of the spark plugs in the combustion chamber. Gasoline engines are primarily the ones that need this ignition system because diesels work on their own internal combustion temperature and they don't need spark plugs. They actually use something called a glow plug. The basic parts of an ignition system include a crankshaft position sensor, a set of primary wires, an ignition control module, an ignition coil, a certain number of spark plugs, and that can vary between different manufacturers. We'll need an ignition switch and then a set of secondary wires. And this is all assuming that the vehicle does still use ignition wires. In some cases we use something called coil on plugs, and we just have ignition boots in those cases. So the beginning of the ignition system operation is when the driver turns the ignition key to the start or presses the start button to power up the vehicle. Electrical current is fed to the ignition coils by the ignition, the engine, or the powertrain control module, depending on the variation that the vehicle has. This current is what energizes coil windings and creates this strong magnetic field. When starting the motor, we turn the crankshaft to make the engine fire. Well, turning the engine doesn't make it fire as much as a crankshaft position sensor that signals the ECU that it needs to fire. And that's an important part of today's modern ignition systems. Years ago, we used to use something called a distributor cap and rotor that would determine when that spark would happen. But today we use crankshaft position sensors. So the next component, other than the ignition switch that we start the vehicle, is the ignition control module, or ICM. And this guy is a control unit that receives signals from the engine control module and the crankshaft position sensor. And it uses those signals to determine when to start and stop the current flow to the ignition coil. It pretty much controls the ground side. It makes the circuit open, preventing current from flowing when it doesn't want to go. The ICM stops that current to the ignition coil, and the ignition coil feeds higher voltage current to the spark plug. This causes that electric arc that we've seen between the two, and this is what lights off that air-fuel mixture. This process is known as induction, where the collapse of the magnetic field induces a higher voltage for the spark in the spark that occurs in the spark plug. So all spark ignition systems have what they call a primary and a secondary circuit. And the primary circuit are all the components and wires operating on the low 12 volt DC system from the battery or the alternator, or current from a high voltage vehicle. The secondary circuit are all the parts carrying the high voltage current. That induced voltage that spikes very high. Wires and spark plugs between coil output windings and spark plug ground are primarily the components that carry the secondary ignition circuit power. This secondary operating voltage typically has pretty thick wires. If you've ever looked at an actual ignition wire, they're usually about the size of a pencil of insulation, and that's all to prevent leakage because of this high voltage that's being carried through the wire to the spark plug. The secondary operating voltages of an ignition system can vary anywhere from 4,000 to 15,000 volts, and even sometimes higher. So they can be lethal, and we do want to take care when we're working around these systems. So when we're thinking about these ignition systems, we want to look at the primary side first and just have a basic understanding that this is the low voltage side. This system's operating on 12 to 15 volts that's being fed to the ignition system, usually via the battery or the alternator once the vehicle's been started. The ignition ECM can sometimes also be involved in this, and on our newer hybrid vehicles that still have a combustion engine, those vehicles would definitely need to have a 12 volt system established to keep those systems running as well. Here's a picture of a spark plug. I assume most of you have probably seen these at one point or another, but this spark plug uses the ignition coil, the high voltage, to ignite that fuel mixture. So these are actually are screwed into the cylinder head in an optimal position to light the fuel air mixture that's in the combustion chamber. You'll notice the spark plug's made of a ceramic insulator, which are pretty good typically, unless they get cracked. So you do want to be careful of these, because if you drop them, you can crack that ceramic insulator. And then we have a steel shell and a hex nut. That's what we actually are able to turn this in and out. Below that, we'll have a set of threads for going in. But the two most important areas that we pay attention to are that center electrode and the side electrode. This is mostly because this is where the spark is occurring, and we can tell a lot by looking at these two components when evaluating a problem on a vehicle. So again, as a review, that center terminal, the center electrode, is what conducts electricity into that actual combustion chamber. And then the side electrode is what causes the electricity to jump the gap and return to the battery. Basically, we got a high voltage that's trying to find the ground side of the vehicle, and so that's why it jumps across and creates that arc. We have that ceramic insulator I mentioned to be careful with. That keeps the high voltage at the spark plug from jumping out past the spark plug to ground and not getting into the combustion chamber. And then we got that steel shell that's there that supports the other part. All right, so the spark plug reach is the distance between the end of the plug threads and seat or sealing surface of the spark plug. So you can see here from these two images, that threaded portion, there's this short thread and there's a long thread. This doesn't mean that they're interchangeable, but just make you aware that they make both variations. This could be a problem if you put a long reach spark plug into a short reach spark plug, because you potentially could impact the top of the piston, and this has happened before. So we want to make sure that we look at the number to determine how far that spark plug extends into the cylinder head before we tighten it down to make sure we got the right plugs. We have also some variations in spark plugs that are what they call resistor or non-resistor spark plugs, and that has to do with the internal resistance in that spark plug. And if it has a resistor, that resistance can be up to 10,000 ohms. And the purpose of this is to reduce static in radios and television sets. Keep in mind that when we use this type of resistor, it puts more demand on the ignition system, because the voltage now has to overcome this additional resistance as well. For non-resistant spark plugs, they have a solid metal rod that forms the center electrode. Much easier on the system, and obviously, depending on what's driving it, if they both had equal amounts of voltage driven to them, the one that has the non-resistor would have the hotter spark at the end, because it doesn't have resistance to overcome. Now, spark plug gap used to be something that was very commonly adjusted by technicians, and that's because the precision wasn't there. So we still check spark plug gap, and that's the distance between the center and side electrodes. And normal gaps range anywhere from 3/1000 to 8/1000 of an inch, depending on what the application is. And you can find this in any service information. Most spark plugs today are typically coming gapped. Still not a bad idea to check them. Make sure that they're at the right length. The larger gaps are used with electronic and computerized systems because those are usually of much higher voltage and they can jump that spark, or jump that gap, I'm sorry, with a larger spark. Another consideration of ignition systems related to spark plugs are the heat ranges. This typically heat range is the rating of the spark plug's tip's operating temperature. And so a hot spark plug usually has a long insulator tip and tends to burn off deposits, while the cold spark plug is a shorter insulator tip and operates at cooler temperatures. Very often we've seen years ago, for example, you would put hotter plugs in vehicles that were starting to get worn, that were starting to burn a little bit of oil, because that hotter spark had to overcome that fuel oily mixture in the combustion chamber. But what's most important about all of this is that you want to make sure that you're selecting the correct plug for your vehicle and not just taking something for granted that someone hands you over a counter. Make sure that the temperature range is appropriate for the vehicle that you're installing it in. And you'll find that most newer cars are using that longer insulator style tip versus older systems that had a shorter thread base on them and often ran much cooler. Now, when we look at these heat ranges, the manufacturer normally recommends that specific spark plug heat range for their engines, and it's coded and it's given as a number on the spark insulator. Larger numbers typically indicate hotter plug tips. Again, for the most part, it's really important that you validate that the parts that are handed to you from the parts counter are indeed the correct application for the vehicle you're working on. And you do that by going into Pro Demand or some version, service information version, to verify that the plugs that you got do indeed belong to that vehicle. So besides the spark plugs, the next thing we take a look at are secondary wires, or spark plug wires, is how they're often referred to in the shop. And these are what carry the high voltage ignition coil current to the spark plugs. They typically have a boot that protects the metal connectors from corrosion, oil, and moisture. That boot slides down over the spark plug and then usually to whatever the system is. Maybe it's an ignition coil pack. Those boots are there to try to prevent any type of corrosion occurring inside those terminal ends. And then the resistance wires are often done because they want to suppress radio emissions that would cause noise. The spark plugs create these magnetic fields that potentially would drive you crazy if you're listening to any type of music on your radio. And so they do this to try to help insulate those spark plug wires to not cause that noise. And as a tip with this, most late model engines have an ignition coil mounted directly to each spark plug. This is often referred to a coil on plug. However, there are systems like you see here in the image where the coil is right above the spark plug area, and there's a small short secondary wire that's in between there. Just depends on the version that are out there. Again, you'll want to keep an eye on these types of wires because often they're next to exhaust manifolds, and that heat can cause these plastic or silicone insulation wires to get hard and brittle, especially if you go in to remove them to replace spark plugs. The action of you pulling on the wire can often cause problems where you get holes or tears in the boot, allowing the spark to go in undesirable areas. Another component we need to be aware of is the ignition coil itself. So we saw the spark plug, then we saw the wire, and the bulk of that electrical signal comes from the ignition coil. These are typically a pulse type transformer that produces a short burst of high voltage to pass current through secondary wires and jump the spark plug. There's two sets of windings that are usually located inside the ignition coil of wire that's very thin, and it causes this high voltage to occur through induction. There's two sets of windings. Those primary windings are usually several hundred feet of heavy wire, where the secondary windings are several thousand turns of very fine wire. And later on, when you learn more about electrical systems, you'll understand what the windings and wires have to do to create that voltage amplification we're looking for. So the open circuit voltage that's involved with an ignition system, on late models, that voltage is jumping to about 15,000 volts, depending on the design and the spark plugs. The ignition coil, the open circuit voltage, has a maximum voltage, is the maximum voltage potential. That can range from 40,000 to 100,000 volts in late model designs. Keep in mind, pretty much in the 80s, you could get hit with a spark plug. If it shorted, you wouldn't risk a whole lot of injury. But today, because of the voltage values, the ignition systems have gotten much more powerful, and they can cause serious harm to us if we accidentally get struck by that electrical current. So looking at the ignition coil operation, current needs to flow from the ICM or ECM and primary windings. This creates a strong magnetic field. That's due to the wrapping of the heavy wire around an iron core that concentrates and strengthens the field. When the current is interrupted, basically the ground side of the circuit is fielded open. The magnetic field that's around these wires collapses, and that collapsing causes the secondary windings to induce have the magnetic collapse induce a voltage into the secondary windings. The high voltage here, as you can see on the items to the right, causes the high voltage shooting out of the high voltage terminal of the coil, that collapse, and then it travels through the secondary circuit down to the spark plug. So this current collapses onto these windings, and it's looking for a place to go. Remember, electricity wants to go the path of least resistance. The spark plug wires in these boxes are all insulated very well, so the voltage is going to travel down towards the spark plug and be attracted to that secondary electrode that's actually attached to the ground of the body, because there's nowhere else for it to go. And that's in a perfect world. Obviously, if the spark plug has a small gap, cut, or fracture in it, the spark, again, will go to the path of least resistance, and that's sometimes known as a misfire that we deal with on a vehicle. There are other variations to this ignition coil design. There's what they call direct ignition system, which is one coil for every cylinder. Very popular today. And part of the reasoning for this is that we put the coil directly over the spark plug. We have a boot now, not several feet of wire for the voltage to go through. We can deliver a hotter spark, a stronger spark with less distance. There's also what they call coil pack ignition system. It still has one coil for every 2 cylinders, and sometimes they'll have one coil pack for 4 cylinders. They're more of a combined ignition coil system. Rather than having one on each cylinder, they just kind of pack individual coils all together for each cylinder. So with the direct ignition coil, it bolts directly over the top of the engine. It fires on only the power strokes for the maximum efficiency. There's one coil for every spark plug, and you can see here to the right in the first picture that the top of the coil is the little block, and the boot is below this. The boots are typically replaceable if needed, as well as the ignition coils. There's 2 primary wires that connect to each direct ignition coil from the ICM engine or the power control module. Those primary wires are what induce, again, the big voltage inside of these style systems. So in these images, you can see some variations of different coil packs that exist. Remember, you can have a ignition coil that serves 2 or multiple cylinders. Sometimes it will be individual coil packs, and sometimes it will be combined ignition coil packs. The one in the middle here that you see is actually using 2 coils to feed 4 spark plugs. This is known as a waste spark system. When you see this design, many engines use waste spark, and that's to minimize the amount of coils that are needed to get the spark to where it's got to go. without having additional cost in production. The spark plug wires, though, are connected from the coil pack to the spark plugs themselves. So on the direct ignition system, we'll have multiple ignition coils, and there will be several engine sensors and computers that are used to fire those spark plugs at the appropriate time. Today's vehicles, this is very common to see direct ignition systems. The coil assemblies are mounted directly above each spark plug, and this eliminates the need for secondary wires. Keep in mind, the longer the wire, the more resistance. By putting the ignition coils directly upon the spark plugs, we've shortened the distance a great deal. We're able to deliver that voltage very quickly on time to those specific cylinders. This direct ignition system uses a computer to analyze the sensor signals and control the ignition timing. The crankshaft position sensor is one of the sensors that's telling the computer where the engine is, what the engine speed is, and what the position of the piston is on any given cylinder. We also have a camshaft position sensor that provides data on where the cam is located, specifically on vehicles that need to advance or retard the timing. There are additional sensors that can be taken into account as well, especially if we're dealing with a turbocharged or supercharged system and we have different manifold pressures occurring. The direct ignition system with an ignition control module, or ICM, are systems that are sometimes used where the ignition control module is actually in each ignition cylinder. The ECM or PCM signals the ICM to fire spark plugs at the correct time. Now, I know that's a mouthful. The ECM is the engine control module, or sometimes it's called a PCM, power control module, that's sending the signal to the ignition control module, the ICM, to fire the spark plugs at a very precise time. The ICM is going to interrupt the current going to the coil's primary windings, and it does that through opening up the ground side of the circuit. It usually is using a transistor to do this, and this causes a high secondary voltage to fire into the spark plug because the primary and secondary windings are contained within that ignition coil. So here's a picture of a waste spark system. You can see on here it's also called coil pack ignition system or computer controlled ignition. And waste spark is theoretically firing two spark plugs at the same time. You both forward and backwards as far as how current will tend to flow. So from the positive to the negative, it'll spark one way, and the other side, that spark jumps through the ground side to the positive side. This is very common on vehicles, especially some of the more economy style vehicles. This helps keep costs down. That secondary spark, though, can be valuable, especially if we're looking for complete combustion. Basically, they can fire these just a split second off of each other so that the residual fuel air mixture is lit, ignited, and burned. The electronic coil module is the coil pack, and that's going to have two or more ignition coils when you hear of electronic coil module. And the coil control unit, or this electronic circuit, is what actually operates the ignition coils inside the cylinder. Each coil in the module serves two cylinders. So that's why it's called waste spark. We're sharing this. 6-cylinder engines here would have 3 ignition coils. An 8-cylinder would have 4 ignition coils. And a 4-cylinder would have what? You got it. Yeah, 2, right? 2 ignition coils. And these are performing pretty much the same function of a separate ICM ignition control module. Here's a nice picture of what's actually going on. In the middle, you can see the coil control module, and that's hooked up to 2 separate ignition coils, which in turn are hooked up to 2 spark plugs. As you can see, that there's a power source, there's a crankshaft position sensor, and a computer that's tied into this control unit. But when the ignition is commanded on, you can see the 2 spark plugs on the right side fire, and the 2 on the left side are not firing. And one of the biggest things to understand is that one of those is firing on the power stroke, and one of those is firing on the, you guessed it, on the exhaust stroke. So that way that whatever's being burned is burned completely and out of the engine system before the new fuel is added to that cylinder. So with this waste spark ignition system, the operation, the computer and the sensors are what send the electrical pulses to the coil control unit. The control unit fires each one of those ignition coils, but because they're hooked to multiple plugs, the secondary output of each coil is wired to 2 spark plugs, so both spark plugs will fire. One spark plug arc produces the power stroke, and one arc does nothing. It's called the waste spark because it's on the cylinder in the exhaust stroke. And then the burned gases are pushed out of the cylinder. Now, you may be asking yourself, and you're probably correct, let's say that a cylinder had a little extra fuel or was running too rich. It's very possible that the waste spark cylinder, the one that's on the exhaust stroke, if it's a rich enough mixture, when it fired the spark, you might get some backfiring out of the vehicle. There are what they call dual spark plug ignition systems out there, which means that there are 2 spark plugs that are plugged into each cylinder on the vehicle. One plug is located near the intake valve and one is located near the exhaust valve. Dual plugs ensure better ignition and combustion of air-fuel mixture. There's been a lot of experimenting going on to try to find out how to light the fuel mixture in the combustion chamber precisely and evenly, and by adding 2 areas of frontage flame on this, we can get a smoother combustion out of that cylinder. We also have multiple discharge ignition systems. These multiple discharge fire the spark plug more than once during the power stroke. They can fire hundreds of times in a power stroke. Again, what we're trying to do is to keep lighting off the flame as evenly as possible. And again, this is really to help ensure that we're getting complete burning of the fuel charge that's been entered into the combustion chamber. This type of system is very common on high-end and racing engines. Some late model engines use this same system with direct fuel injection together as a complement. So in other words, the ignition system can fire multiple times and the direct injection of fuel can be fired several times, all within one power stroke, microseconds apart from each other, to create almost like a torch effect burn. So the engine control module, or ECM, has a controlled sequence in which the spark plugs are determined to fire in the combustion chamber. Sometimes, this is part of what they call engine timing. So you want to make sure, even though we have some pictures here, not every engine is set up this way. I highly recommend whenever you're trying to identify the cylinders that you use the proper service information to determine which cylinder is indeed number 1, number 2, number 3. But looking at the sequences, for example, on the 4-cylinder, number 1 would be the first cylinder fired according to the coil pack below. You can see the firing order is 1, 3, 4, 2. So number 1 fires first, then number 3, then number 4, then number 2. And then if you go down to the next one, there's again some differences. So one is what they call cylinder identification, and the other is called firing order. And so when we're running our ignition wires, specifically with old distributor caps, this can get a little bit confusing. You got to make sure that you're running the wire to the right cylinder in the ignition sequence. Another important issue is what they call ignition timing or spark timing. How early or late spark plugs fire in relation to the position of the engine pistons, sometimes called advanced or retard. And so below here you can see the timing advance, and that occurs when a spark plug fires sooner during the ignition compression stroke than it's intended to. And that's usually done at higher speeds of the engine. So in other words, when you start off from a stop sign, typically your engine wants to advance the timing to get the engine to rev up quickly. The timing retarded position is used for cruising, right, at higher speeds. And that occurs when the spark plugs fire later in the compression stroke, and they're usually at lower speeds under high load conditions. This is typical at highway speeds to give us a good complete burn. With these spark advanced systems, right, the engine sensors, the ignition control module, the powertrains, all can adjust the timing based on various inputs. Some of the main sensors that you need to be aware of that controls where the spark happens is the operating conditions. Is the car under a hard load or a light load? And it sends that data to the computer, and the engine control module analyzes the data to determine where it should change the timing for maximum efficiency. There's a lot of different sensors that are involved in this process, and that has to be done very quickly and accurately by the ECM. Here is a list of the sensors that have the greatest influence over ignition timing. And again, there's other sensors that influence this as well. Our crankshaft position sensor is a critical sensor that we need for the engine to run. Camshaft position sensors are involved. The manifold absolute pressure sensor, if you have a MAP sensor style vehicle. Intake air temperature, whether the air is cool and dense or hot and not dense. Engine coolant temperature sensor, super critical, depending on the mixture that's going to be happening. We got knock sensors telling us about when detonation is happening. And then again, that throttle position sensor is telling us what kind of load we're trying to place on the engine. Looking at these sensors when you're dealing with some kind of issue related to ignition is usually part of the initial visual inspection before we actually go in and start testing anything. Very often, one of these sensors may have a problem that's causing issues with the timing of the vehicle. All right, that should give you a good overview of the ignition system and components. Now, there's a lot more to it that we get into further classes, but those are the basics. If you have any questions about any of that, please feel free to reach out to me so that I can clarify any area that may not seem correct. And once again, thanks for listening and watching, guys. I appreciate it. Hope you found this helpful.